Okay, so in this next example, we're going to look at L'Hopital's rule applied to a limit. So you can check when with this quotient here, you can check that if you were to plug in 2 plus I, what you're going to get is 0 over 0. So I'll leave that to you to check that. And so this should look familiar. This is usually called an indeterminate form, which is it's not necessarily the case that it doesn't exist. It matters how the functions approach it, how they get close to 0. And if we encounter these indeterminate forms, then there's the familiar formula for trying to compute them a separate way using L'Hopital's rule. So L'Hopital's rule says the following in the context of this class as a reminder. This is a theorem. If we have two functions and they're analytic at some z0 and f of z0 is the same as g of z0 is 0 and g prime of z0 is not 0, then the limit as z approaches z0 of f of z over g of z, which if you plugged in z0 you would get 0 over 0, is f prime of z0 over g prime of z0. Okay, so let's apply this now, apply L'Hopital's rule to this limit. All right, so let me rewrite the limit real quick. So that was z squared minus 4z plus 5 over z cubed minus z minus 10i. All right, now it is the case that, let me write it like this. It is the case that if we let this be our f and this and the denominator be our g, then we do know that we do know a couple of things. We do know that f and g are entire, so analytic everywhere. In particular, analytic at 2 plus I. So again, entire means you can take the derivative at any point. F and g on their own are just polynomials. Polynomials are the best functions. You can differentiate them to your heart's content. There's never any problems differentiating a polynomial. We also know, so that's that first condition. We checked this guy. Now we have to check this one. Well, I leave that to you, but f of 2 plus I is going to be g of 2 plus I is going to be 0. Great. And now the last condition is that g prime of z naught needs to be not 0. So let's compute g prime of z. So that's 3z squared minus 1. And let's plug in 2 plus I into that. So that's 3 times 2 plus I squared minus 1. That's 3 times 3 plus 4i, I believe, if you were to do that. And this should give us 8 plus 4i if you were to do the 8 plus 12i rather, sorry, if you were to do the arithmetic. All right, great. So this limit then is going to be f prime of 2 plus I over g prime of 2 plus I by L'Hopital's rule because we satisfied the conditions and the denominator was not 0. I guess we have to compute f prime of 2 plus I. So let's scroll down a little bit more to do that computation. So f prime of z is going to be 2z minus 4. So f prime of 2 plus I is going to be twice 2 plus I minus 4. And I think if you compute this, you'll find you get 2i. So we're going to get 2i over 8 plus 12i. And that's, as far as I care, this is a perfectly acceptable answer for the limit. But if we wanted to, we could rationalize, and you'll find you get 3 over 26 plus 1 over 13i if you carry out the complex division.